Welcome on and all to the Math Magic Show. In this one we're going to learn how to transform e to the x into the ln x function. So let's get going. The first stage is to graph e to the x. So this is perhaps a bit of a reminder, but it basically looks like this, and this is e to the x. Let's review a basic concept, which is the following. When you grab a value of x, for example, from the x-axis, so down below right here, as you can see, I've selected x sub 0. That just means a particular value of x. When you feed it into the function, it comes out on the vertical axis as y equals e to the x sub 0. Again, e to the x sub 0 is just a number in a disguised kind of form. Keep that in mind. Just out of convention, we usually read graphs, say, from the horizontal to the vertical, but there's nothing special about that. Nothing in nature that says that it must be done this way. We can do things any way we want, essentially. It's our world, after all. So what we can do instead is just read from the vertical back down to the horizontal. So in other words, read it this way. Take a look. Let me delete those, and I'm going to emphasize this. I'm choosing a value of y. That's my input now. I'm going to pass that into the curve and then pass it out on the x-axis down below. So as you can see, this is now renamed ln of y. So the y's are my inputs and the x's down below are my outputs. So y sub 0 goes in. It basically passes through the curve and this point here, and then comes out down below as ln of y sub 0. So when you read the graph this way, it's the ln function you are essentially reading. So the e to the x and the ln functions are deeply related in a sense. It's really the same function if you think about it, but depending on how you choose to read it, you either call it e to the x or you call it ln x or ln y in this case. Now let's investigate some additional details. These are kind of interesting. So let's go back to this previous view for a second, where x sub 0 is the input and e to the x sub 0 is the output on the vertical. And take a look at these little line segments that I've drawn right down below. What are these little line segments? Let's zoom in on them. So take a look. Notice that the graph always seems to keep a distance from the horizontal axis, from the x-axis in other words. That's indicated here with this double-ended arrow. It's also indicated with a smaller double-ended arrow. And if I scroll over through my little world here, you see there's always a distance between the graph and the x-axis. And notice that I've colored over the x-axis with a yellow dashed line. So when you approach a line that you can't actually reach, that's called an asymptote. So we would say that the x-axis is the horizontal asymptote for the curve e to the x, a virtually infinitesimal gap between the graph and the horizontal x-axis. It's always there, it's always present. We just can't see it at some point, but it still would be present. Maybe it would become quantum at some point. But let's move on. So keep this in mind. The question then is, how do you interpret this horizontal asymptote in the context of the ln function? That's the question to be answered. How can we go about that? Take a look. What we can do is just flip things essentially. It's a little bit interesting. So now I've switched my perspective. It's as if I were again going back to feeding values from the y-axis and not putting values on the x-axis. So I'm putting y sub 0 in and getting out ln of y sub 0. What I'm going to do now is kind of illustrate what happens to that horizontal asymptote. As you can see, this looks like the e to the x function. If you want to make it look like the conventional ln function, we wouldn't leave it in this form. So the next step is just convention, to make this conform to the normal way that the ln function is usually depicted. So we can do that simply by spinning it. Take a look. First, I'm going to spin it this way. And you see how that horizontal asymptote has become now a vertical asymptote on this side. So maybe I should reverse that. And now I'm going to spin it one more time. Take a look. That's the next step here. When I spin it one more time this way, now again, what was originally the horizontal asymptote on e to the x has become, as you can see here, the vertical asymptote on the ln function. And now that purplish curve actually does look like the standard ln function, which is beautiful. That's what we wanted to do. We want to illustrate the connection between the two. This is probably the best way I know how to do it. This is equivalent to, say, like basically taking a piece of paper, drawing e to the x and flipping it a certain way. Across the line, y equals x essentially. Flipping the piece of paper kind of this way, and it's going to give you the ln curve. That's a common way of showing the relationship between functions and their inverses. And the e to the x and the ln functions, the natural log functions, are inverses for that reason, the way you see it here. Now the last bit would be to relabel things. Again, because of convention, you wouldn't leave the horizontal axis called y and so on. So what I'm going to do is this. Take a look. I'm going to rename my input x sub 0. I'm going to therefore rename my output on the left side now ln of x sub 0. The horizontal axis would now be renamed x. and the whole graph would in fact be renamed ln of x. This would be the conventional way of depicting everything. So what I wanted to show you in this video again is the important relationship between e to the x and ln x, and the fact that essentially, if you know what you're doing, the e to the x is both graphs. As long as you learn to read them either from the horizontal to the vertical for e to the x, or the vertical back to the horizontal, and that's a kind of underlying relationship between many functions and their inverses. Thank you so much for watching. Please leave a like and subscribe. I'll see you in another mathemagical video.